Hey guys, welcome back to another episode of the Real Hacker Hours podcast. This is basically where I just do the normal side project work I typically do. I just hit the record button before I do it. Today, we're going to be continuing the same thing that we have been doing for the last few podcast episodes. I made a tool that effectively just wraps semgrep, which what semgrep is it is a source code auditing tool designed to find bugs. You can write rules for it and it'll look for particular code patterns and flag it. What I'm wanting to do right now is I'm wanting to effectively evaluate how effective it is. So I'm just going out and using it against various code bases and seeing if it can find anything. And if it finds tons of bugs in tons of different code bases, good chance it has a good level of efficacy in some regards. I know last few code bases I've looked at have been HTTP, and I found a lot of success with that. So I'll be continuing with that. Right now we're looking at this project right here, and we can see here we found some stuff here. Found rows flag. Looking at these, the ones I probably care about the most, sprintf, stircopy, and stircat. Just in my experience, those have been the most. Those rules lead to the most um greatest chance of getting an actual like RCE or code execution. So I'm going to take a look at those, starting off with sprintfs. Okay, most of them are httpd.c on these lines. Let's see. httpd.c, line 11. Oh, no, it's response. Okay, 113. Let's see what's here. File path. Okay, so with an HTTP request, what it'll be doing is typically will be to a particular resource. I believe that the path and URL are derived from that. So it'd be reasonable to guess that we control the path in the URL. File path, we see that is a char array right here for 255 bytes. So if we control path in URL and there aren't any size restrictions, this alone should be a buffer overflow where you can overwrite the return address. Let's see. File path URL. Where does that come from? Can we read client size? Yeah, path and URL. URL comes from there. Where does path come from? Okay, path is a global variable. One thing I just noticed that seems like this would be a pretty obvious bug. This char right here has a size of 1024 bytes, which is obviously way bigger than file paths 255. So if you just have a large enough path, that might be it. Also, a path might be the direct web directory of where the actual website is. And where does URL come from? URL appears that it just gets parsed from the request. So I'm just going to try. It seems like the request itself might be enough to execute a buffer overflow. I'm just going to go ahead and try that. And let's see. It's going to build GDB mini HTTP disassemble accept request. Let's break it, accept request, and run it. Okay, server needs a server directory, and I'm gonna make dub. what was the syntax again? Server directory in the port. Server directory is that. Port is this. It needs sudo privileges with my current permission set up. What is this? This is accept request. Let's set a breakpoint for here. And let's run it. Nope. That's from the work I did yesterday. I believe it's running. Okay, cool. Let's try to send a request. Port 80. Although port 80 don't need to do that. It's default. Okay. So we can see here that we can just hit it via just sending a single request. Let's see exactly where the sprintf is happening. I'm going to copy this into another tab so I can just quickly parse through it. Sprintf. There's only one sprintf. Okay. Let's see, where is that in the assembly code? It is here. Let's set a breakpoint for here. Info B, delete 1, break there. And we see that the request we specified in our request, the resource we specified in the request, which that's the 159.357.2a, is one of the two sources for it, and the second source is the web directory itself. So we know that the size of this char buffer is 255. I'm just going to try sending it a giant, just a giant string that's 1,000 bytes, since that should overflow it, assuming that there are no size checks. So let's try that. We are here. Okay, it looks like it got the full, let's see, how, 1,000 times, yeah, it looks like it's full string. Let's see, does this overflow it? We see there is an RIP that looks like it's valid. Step in, finish, some printf. Okay, that didn't do it. Okay, let's take a look here. So let's see, where is our destination? Is this right here? Let's see, how far away from the from the return address is this? RIP's there. How about 5,400 bytes? Does that make sense? It's writing it to file path. So looking at the stack frame here, we see that buff is about 1,000 bytes, and there are a few 255 byte values, so it makes sense for it to be like 2,000 bytes, maybe, depending on the exact stack alignment. But 1EC5. Actually, let's take a look at the assembly code for this function again. So we can see that sprintf, this is the call right here. RDI gets 1EC5. Okay, so this is a giant call stack. Okay. So the size is around 5,400 bytes. I'm just going to try sending 10,000 bytes and see what happens. This read line right here, it seems like it will scan at a maximum size of buff, which is 1,000 bytes. So you might only be able to scan in 1,000 bytes, but let's see. wget 127.0.0.1 slash. Okay, let's see how many bytes do we actually have here. 1,019 times. All zeros make sense. Okay, cool. So we won't be able to overflow it that way unless file path. One thing I'm just going to try real quick. I'm going to try. You see that path is a buffer of 1024. I'm just going to try giving it a massive buffer since we've seen in previous projects that will actually lead to an overflow. And it does. In main. Okay. Source, is it here? Looks like star copy in main. Main. Let's break here. Pi break at there. Pi run. Let's copy this over. Here we see what looks like a normal stack frame. Step in, finish it. Let's check the memory mappings. B0, what is the max? Okay, cool. So what it looks like is we have an overflow of the BSS section. So right now, path, this is stored in the BSS section since it's a global variable. That way it can be accessed from different functions. Thing is, it's copying straight from argv, which is an argument passed in without any size checks, so that by itself is going to lead to an overflow. This isn't of the stack, it's of the this region of memory. And we see here this region mapped memory goes from 54 to 55, 55 to 58, 58 to 59, 59 to 5A, 5A to 5B, and it's trying to write to 5B033, so it's trying to write past the end of this region memory. Also, the global variable section is entirely in this. I can tell that because it's the memory permissions are RW. So yeah, it's overflowing that region and writing past the end of the mapped area, so that's where it's crashing. Yeah, it's not smashing the stack, it's just exiting with a segmentation fault. Okay, so that's one bug. I want to see, did my semgrep tool find that? Nope, wrong. Oh, I'm just going the wrong directory. It's here. No. There we go. Rules flagged. Star copy. Line 342. Star copy destination static. Okay, it does not appear like it found it. Yeah, this is httpd.c line 342. Looking at store cat and store copy destination static, which these are the only two rows that deal with store copy. I'm not seeing at flagged, probably because, let's take a look up here. Maybe it's a thing where it's having a hard time find the roles I made are not able to find things in the BSS, but I'm not too sure of that. But I found, okay, this tool missed a bug that I should have found. I will now make a change to that. And yeah, I'm going to pause the stream for a second. Okay, cool. So yeah, we found one bug that we were able to actually cause it to have a segmentation fall. We see some other things that look a bit promising, so let's try with that. First thing I'm going to try and do is see if I can't get this to actually, this sprintf that we're originally looking at to give us a crash. Now, how we could do that in theory is we could make this path, oh yeah, this path char pointer, since we specify that with command line options, we can make that something super big so that it will fill in the gap entirely and not allow URL to actually overflow it. For that, what I'm going to try doing is having the zeros that we print instead of 10,000 only have 5,000. And now if this will work or not will depend on how like the compiler actually puts together that section of memory. I'm not sure, but let's see. And yeah, that doesn't work. If this, I'm now decrementing it to only 4,000 zeros. Since the gap between it is between the destination file path and the saved return address on the stack is around like 5,000 if I recall correctly, and the max URL size is 1,000 bytes. If path can't at least be 4,000 zeros, then I don't think we can actually use this for a buffer overflow of the saved return address. But let's try that. Okay, yeah, that's with 4,000 zeros, we're still hitting the original star copy bug here, which is causing us not to be able to leverage that sprintf. So effectively what we're seeing right now is, ideally, I think personally, if this star copy bug wasn't here, that sprintf would turn into a BOF. But we're seeing here, it's one bug preventing us from getting to another. So let's take a look at some of these other sprintfs to see. Line 277, let's take a look there. Okay, cool. So we're seeing here is this is the functionality for execute CGI, which that's like a functionality with HTTP to execute certain types of scripts. I forget the exact specifics of it. It looks like here that it is copying some things that are specified from commands in it. Let's see. URL is that, where is execute CGI specified from? Let's take a look. What is EX? So file path equals that. Okay, it looks like it's wanting. So it looks like here it'll either serve a file or execute CGI, so it's a choice between them. Depends on EX, which EX is set here. Okay, so it looks like if the extension of it ends with PHP, it's going to hit execute CGI. Let's put that hypothesis to the test. Execute CGI. wget 127.0.0. Not found. Okay, so it actually needs to have the file. See that because of this right here. If real path, then do this, which HTTP not found, and I'm assuming that just checked to make sure that the file actually exists. And also, I got that if a file has the .php extension, it will call the execute CGI from here. We see here there's a store copy, not store copy, store compare with what looks like the final 3 bytes of the file path in PHP, and if that's equivalent, it will say ex equals to 1, which means that this will run. So now that we've got that, let's just touch that. So we have strife.php. Let's now see if this will do it. Break at execute CGI. 80. Forgot. Need sudo to run this. And let's try this. And we hit execute CGI. Okay, so that was, even though the script file is just empty, the fact that the file exists and that it ends with PHP, I'm not sure if we need the dot. That is enough to execute CGI. So let's take a look here. You can see there's a lot of sprintfs later on. Find the content length. Looks like there's some additional checks here we may or may not by default get through. I'm gonna see if we do by setting a breakpoint for sprintf. What are the arguments? HTTP, okay. So this is that sprintf right there. Looks like that is the only. Let's see, what does strife.php give us? Nothing. PID equals 0. What does PID come from? PID equals fork. Oh, okay, I think at this point is when it detaches and spawns a child process, and we'll need to look at that. So let's continue. Let's send another response so we can hit that code path. Set follow fork mode child. Cool. And break at sprintf. HTTP, okay. Script name equals. Okay, cool. So we see here strife.php. Script name. Script file name, which we see right there, equals path. Request method environment. Where does it? See sprintf right here. It's writing into sprintf name environment, sprintf file name environment, method environment, query string environment, and content length environment. Where is this defined? Let's see. Oh, these are all char pointers. Okay, cool. What I'm curious of is, let's see. Script file name equals. How far is the, so these are all in the stack evident from that right there. I'm curious how far these are from the return address if we have an overflow and we can actually reach the saved return address. Since that will prove that this is a bug. RIP at there. And the destination is here. C6A, about 3,000. If we have like a 2,000 or like a 2,500 byte directory mixed with like a 1,000 byte file name, which we can get that from receipt, we should be able to cause an overflow with that. But let's keep seeing if there's something closer we can use. Bin bash, don't have any control over that. Query string equals, don't have anything with that. Okay, cool. So let's see. Will a 2,500 byte directory cause that sprintf bug in the beginning to crash? Nope, it will not, apparently. ps.ax grep. What is this? Mini httpd. Okay, looks like it is over with. Let's set a breakpoint 4. Actually, let's just run this. 80. Sorry, I'm going to pause the stream for a second while I fix this. Okay, now continuing the stream, let's try this. 80. Okay, cool. You see that we were able to have a directory of 25,000 bytes. Let's set a breakpoint for execute CGI. And let's try doing this. Sending 2,500 bytes. I know not all of these will get past the size check since it only scans in like 1020, but it's going to scan in 1020 bytes anyway, which is what I care. Oh, I messed up. I mistyped the IP address. Let's. So, good news. They found a stack smashing bug somewhere. Let's see where. Accept request. So, yeah, we see here the stack smashing. So we have a bug in here that we can exploit. Looking through here, what does it, let's get this entire function. Where does it end? Ends here. Let's see, where does it appear that it could overflow? Read line, probably not there, since it has a size check there. Does not equal method. Could be here. Reason, this is effectively like a star copy that goes until, well, I is less than n. What does n equal to? Yeah, it could be this right here that overflows it. But I believe it's an accept request. Reason for that being is you're seeing that there. So I'm gonna set a breakpoint for there, and let's try it. So we're here, disassemble. Go all the way to the top. Read line. Okay, this is that right there. Actually, I'm not gonna move them side by side. Let's see, where's the loop? Jump if equal to 242. So it looks like this right here roughly is the loop. Right after that is does a few other things. And what I'm going to do is going to break on read line, verify that that's not causing the overflow, then break on string compare. If there's an overflow between read line and star compare, I know that this is causing the buffer overflow. And let's check to see that. Break there, continue. Yeah, I'm here. Yep, that did not cause it as expected. And let's see. Where is it? String compare. If overflow happens by the time it reaches this breakpoint, overflow did not happen there, so this loop is not causing the overflow. Cool. Let's step through here. Yeah, that string compare definitely is not causing it. I don't know why I checked that. This could be causing the overflow, but I don't think it is. Let's set a breakpoint for this sprintf. Well, I should probably set a breakpoint for this store compare. If there's a buffer overflow, then it's this loop that's causing it. Let's see where that is. Right now, where are we? Right now, we are here. This string compare is probably the second string compare right there. So we'll probably be looking for a string compare later on. Here, this looks like the string compare. So this string compare, I believe, correlates with, where is it? This one right here. So we're basically going to be going from here to here in the code, and there's an overflow. Looking at the code, the only thing that really looks like that could be done is this right here. So it'll be that piece of code right there. So it'll be breakpoint there. Yeah, the stack has not been smashed yet, so we're here, no overflow yet. Only next thing I can really see causing overflow is the sprintf, so let's see. Where is that sprintf? This is the only sprintf in here, I believe, so should be fairly easy to find. It's calling the assembly code. Sprintf right here. Okay, we see what looks like a normal call stack, so we step in, finish. Okay, cool. So it's very evident that that sprintf itself is the one that's causing the buffer overflow, since we saw that the call stack before it was fine, but after it can clearly tell that it's been overwritten, we smashed the stack. So turns out that this bug, I was wrong earlier, we can't actually reach it and cause it to deliver us a stack overflow. So let's also take a look at it prior to us stepping in. Except to crest sprintf. Yeah, it looks like the combination of those large directory and the large file name was enough to overflow it. Just my earlier calculations were off. So in conclusion, we found two different buffer overflows. There's the one that is caused by just you giving it a super large directory name as part of the command line arguments, which is right here. And then there's the one that's a combination of a not super large, but like notably large directory name and a large request object as a part of your HTTP request, which is not there. Where's the sprintf? Right here. So we found two buffs. I think this is a good spot to end. Thank you for watching and see you next time.